Stabilization of native folded protein conformations is a frequent goal in projects that deal with affinity optimization, enzyme design, protein construct design, and reducing the size of functional proteins. One way to stabilize a protein is through the introduction of disulfide bonds. In this video exercise, we'll demonstrate how to run a cysteine mutation calculation to locate and rank possible disulfide bonds using the protein 1VHU, which I have here on screen. Now, this protein already contains one disulfide bond, bridging residues cysteine 111 to cysteine 154. Now, in the first part of this exercise, we'll mutate these cysteines to alanine, and in the second half of the exercise, we'll run the cysteine mutation calculation in an attempt to repredict the cysteines and the true disulfide. This way, we'll be able to compare the predicted disulfide versus the disulfide from the X-ray crystal structure. So let's begin with the protein preparation panel by going to Tools, Protein Preparation. We'll use the default settings for pre-processing, but we'll check on Fill in missing side chains using Prime to fix the missing side chain residues. Then we'll click Pre-process. Now it looks like there are some residues with alternate positions. We'll just click OK to use the current positions displayed in the workspace. Next, on the Refine tab, we'll click Optimize in the H-bond assignment section. Optimizing the hydrogen bonding is important because X-ray structures do not usually have enough resolution to fix the orientation of terminal amides or histidines or the orientation of hydroxyls and thiols. Once that's done, we would normally click Minimize to alleviate steric clashes and relax the side chains, but because we want to repredict the true disulfide bond in this protein, we first need to mutate the cysteines to alanine and then perform minimization. This simulates treating the protein as if it always had alanines instead of the cysteines, and therefore eliminates any pre-configuration memory in the structure for the disulfide. So we'll go to Tasks, Residue and Loop Mutation. Then we'll scroll through the sequence view until we find the first cysteine of the disulfide bridge, and then select it. This also selects the cysteine in the workspace, so we'll choose Workspace Selection. We're mutating this to alanine, so we'll confirm that this is indeed the case, going from cysteine to alanine. We'll use the default refinement options, change the job name, and then click Run. Once the job's done, we can zoom in on the mutation and confirm the cysteine is now an alanine. We'll repeat the process for the other cysteine, but first we need to reset the panel in the Settings menu. Okay, now that we have our mutated protein, we can finish off the protein preparation process by performing the minimization. Once the protein has been minimized, we are ready to perform the cysteine mutation, so go to Tasks, Cysteine Mutation, and then click Analyze Workspace. Here we can see a table of all the possible residue pairs that have the potential for cysteine mutation. So for example, the first column shows the residue pair and what it's going to mutate into. In this case, 2 cysteines to form a disulfide. Here we can see the original residues and their position, as well as other properties that we can use to filter against, such as the beta-carbon to beta-carbon distance, which if you look down here is set to a cutoff of 5 angstroms. So here we'll just display X to X, i.e. non-cysteine residue pairs to be mutated into cysteines. Now, because the protein has no disulfide bridges, there are no candidates for removing the bridge by mutation, but the analysis would identify such cysteine to cysteine pairs if they were present, and this is where you can select them for mutation if you wish. Now, we won't mutate all possible residue pairs in this exercise. Instead, we'll just keep the mutation selection to conservative, so only glycines, isoleucines, leucines, valines, and alanines will be mutated to cysteines. We'll keep the minimum sequence separation pairs at 2, but we'll lower the beta-carbon distance cutoff to 4 angstroms. Notice that this further reduces the number of eligible residues for mutation. There are 3 more options available for us to set, such as restricting the residues to have a minimum B factor, or to be located in a particular secondary structure, or to have a specified solvent-accessible surface area. However, we won't adjust any of these settings here. Again, this protein doesn't have any cysteines to mutate into, so this option here does not apply. Now, for the best accuracy, we've found in current validation studies that using a minimization shell of none, i.e. only the residues involved in the bond are minimized, or including residues that are 1 position away in the sequence gives good results, provided, however, you use implicit solvent. A larger shell of 5 angstroms can introduce a little bit of noise, but the take-home message here is to use an implicit solvent. Once the settings are all set, we'll choose a job name, And something we should have done earlier is the all-important step of actually selecting the residue pairs to mutate now that we've adjusted the eligibility criteria. Okay, when ready, click Run. Because we only have a few residues to mutate, the job should last a few minutes. Had we kept all the default number of residues, the job may have taken up to an hour on a single processor. Keeping in mind that using an implicit solvent does increase the compute time significantly. Once the job finishes, we'll see the results in the Results tab. Let's sort the residue pairs by the weighted score column. This score represents a combination of residue interaction and strain energetics, as well as geometric filters. Now notice that 3 of the mutations have a score of around 400, while the other 4 have scores around 10,000. The 4 large scores have an offset added because they fail to meet one of the cutoff criteria, such as the change in interaction energy to be less than 5 kilocalorie per mole, or for the strain energy to be less than 35 kilocalorie per mole. The good news here is the original cysteine pair, which became the alanines, is ranked at the top. Let's do a quick comparison by bringing in the original X-ray structure. And then notice here that the predicted disulfide in red closely resembles that of the X-ray structure disulfide.